Okay, so we're going to move on to average rates of change and instantaneous rates of change, and we'll talk about what those mean in the context of calculus. Okay, let's start with the average rate of change. Okay, we learned from um, way back in Algebra 1 that the average rate of change, okay, is usually the slope of a line, right? If I take a line and find the slope of that line, uh, that that will give me the average rate of change, usually between 2 points, right? And if I have a function and I want to find, well, let's see, how fast am I going from A to B? If I have from A 2 points, A to B, and I want to see, well, what is the rate of change from A to B? What I can do to estimate that rate of change is I can draw this secant line. Okay, this line is called a secant line because it's passing through 2 points on my curve. Okay, that's just the definition of a secant line. And the secant line will then give me the average rate of change because I can find now the slope of that line. Okay, so it's an estimate. It's not an accurate. It doesn't accurately tell me exactly what's happening all the way from A to B, but it's just telling me the endpoints. It's giving me an estimate of what's happening. On average, from A to B, it's saying I'm moving at this slope, at this rate of change. Okay, and so we can say the slope of the secant line is the change in y over the change in x, and this is just our slope formula, right? Rise over run. Okay, this is rise over run, right? F of b minus f of a, the y value at the point B is f of b minus the y value at point A is my change in y. Rise, that's my rise over the run, the distance from B to A. Okay, the distance from B all the way to A, the change in x. So that is the slope of the secant line, and it is an average rate of change between the points A and B. Okay, but it's not accurate, right? Why isn't it accurate? Because it doesn't tell us exactly what's happening on this line between A and B. So like, what if I wanted to find the rate of change right here? This line does not tell me how fast I'm moving here, or here, or here. Okay, so because it's only giving us the rate of change on an interval, it doesn't tell us the rate of change at a single point. Okay, and that's what instantaneous rate of change does for us. It tells us the slope, or sorry, the rate of change at any single point. Okay, so that's really nice. We want to be able to find this instantaneous rate of change. This is okay, but it's still just an estimate. It's not accurate enough for all of our purposes. Okay, all right. So let's take a look. Well, what can we do about this? Okay, well, we need let me talk more about the tangent line first. So if I want to find the instantaneous rate of change, then what I can do is I can take a point, create a line that just touches this f of x, right? If I can create a line, a tangent line at that point, then I can say, well, right at this point, that's telling me how fast I'm moving. That's the slope of the tangent line is telling me how fast I'm moving right at that point. Okay, so that's what instantaneous rate of change is. It's the slope of the tangent line. All right, the slope of the tangent line is the instantaneous rate of change. So let's mathematically show how to get this tangent line and why that is. Okay, so what I'm going to do is I'm going to take the slope, the secant line, which passes through A and B, and I'm going to try to move B closer and closer and closer and closer and closer to A until that interval, A from A to B, that distance, becomes very small, right? So let me show you what I mean by that. If I were to move this point B to right around here, okay, you would see that the line being drawn is going to go from here to there. Okay, so that's really nice. that line right there is closer to my instantaneous rate of change. It's a more accurate, it gives me a more accurate rate of change between this point and this point. Okay, it's closer, it's a better fit to this blue line. Okay, well, what about if I want to find the instantaneous rate of, what if I move the point B closer? Oops, sorry. Okay, if I move it closer, well, now I'm getting very close to my tangent line. Okay, now I have a line that goes through those 2 points like that. So you can see my line is getting closer to the tangent line. Okay, and that's what I want to do. I need to go from the slope of the secant line to the slope of the tangent line. And we're going to be able to do that by using limits. Okay, so let's start with the formula for the secant line. This is what we had earlier. Well, as I change my B and get it closer to A, I should be able to get the slope of the tangent line. And that's exactly it. The slope of the tangent line at the point when x is A, right at this point, the slope of that tangent line is m sub t, okay, where this is m sub secant, the slope of the secant, this is m sub t for tangent. The slope of the tangent line is the limit as B approaches A, right? As I get this B closer to A, well, then the value that comes out of this expression, which is the slope, okay, will be the slope of the tangent line. Okay, and that makes sense, right? So hopefully you can relate the slope of the tangent line to the secant line. Okay, and that, what does this tell us? Again, the slope of the tangent line tells us the instantaneous rate of change at a certain point, certain x value. Okay, tells us the instantaneous rate of change at a given value, I should say. Okay, value of x. All right. So that's going to be really, really helpful in understanding differentiation. Okay, and this is a new word here, differentiation, and we'll talk about what that means. Okay, differentiation from first principles. So let's talk about first principles. Okay,